I think, in particular, as we start out this unit, today the questions are pretty straightforward. They're going to maybe seem simple, but this stuff is not necessarily simple. And there's some really key techniques, ways of thinking, habits that you have to get into that I think is just going to really like help. Okay, so that's really what today is about. And so it might seem like I'm over explaining things, but it's because I know that as the questions start to get more complicated, that these habits and tips and steps or techniques or whatever you want to call them will be key to being successful in this stuff. Okay. And again, it might seem simple, but just the idea of thinking about what a rate is. It's funny because I just had this exact same conversation with my grade 9 class. In fact, I'll show you our lesson, and some of you might even remember it because it's probably similar to when you were in grade 9, if you had me as a teacher at least. And, it's frozen. And like talking about what a rate is and talking about the units of rates. And in grade 9, obviously, it's a more simple idea, but it's the same thing. And we take for granted what a rate is and what it means. And it's a simple idea, but if you dig into it a little bit deeper, there's sort of more going on. And I think we had some of this conversation in MHF as well at the end when we talk about rates. When we talk about average rates and we talk about instantaneous rates, that was your introduction to that important fundamental idea of calculus, instantaneous rate of change. Okay, and so we're kind of going right back to that and thinking about this again. So somebody give me an idea of a rate, like units of a rate. And then what would you call it? Meters per second. And that is a speed. So right away we see some rates have a word for them and then a lot don't. Some are easy to explain with words and some aren't. They're just easier to think about in terms of their units. But we see right away that a rate is always something per something. Something over something. Usually different kind of units. What's another one? Nice. And that one also has a word, acceleration. That's a rate that's changing. That's a tricky one. We won't see that very often. That could be the next step to this stuff if we did this longer, I guess. But that one is a rate that's changing. The speed, which is a change in distance over time, and then acceleration is the change in speed over time. So the change of how the distance is changing over time. Yeah, so you could take this as far as you want and continue to go deeper, and this would be taking more and more and more derivatives. We're not going to, but yeah, same thing. So you could do change in acceleration over time. That would be very complicated. What are some different kinds of rates? What's another common speed unit that we use? Kilometers per hour. So this is distance traveled. And this is time passed. And this is a change in distance. And this is a change in time. Kind of the key idea is both are changing, right? The distance is changing as the time changes. And in the same amount of time period, if more distance is changed, that's faster speed. If less distance, that's a slower speed, that kind of thing. Okay, good. So those are some good ones about speed. What are some other rates? I think you would identify them if they were given to you in a question, but then coming up with them yourself for some reason is often hard. What's a rate? Another rate that you see in the real world. How so? If it's like newtons that are being used or something per second, yes, sure, it could be. Yep, newtons per second or Wouldn't be new. Yeah, anything over something else would be, yep. Can you think of another one that's common? There are other ones from physics for sure. So how so? Yeah, so dollars per item, if it's the kind of thing that you would buy lots of. What's another one that's cost involved? There's a few other common ones. Yeah, good. I like that one. Dollars per pound or kilogram. So if you're buying something in bulk, yeah, good. Dollars per hour. So that would be like cost or earnings. If you have a job, you earn a certain number of dollars per hour. Or if you're paying for some kind of service, dollars per hour, or paying for, I don't know, time spent in an arcade or something might be dollars per hour. I don't know, something like that. Okay, any others? Somebody had one this morning in terms of moles, something with moles. What would that be? I can't remember what it was.
Just like maybe like a conversion factor between how many moles of something are in like a substance compared to how much it is like a mole.
So it would be like grams per mole?
Yeah.
That's what it was, right? Yeah, so grams per mole, right. There's another one that, oh, go ahead.
Voltage is like, I can't remember the two things. I think this one is change in energy per cooling. I'm not sure.
Yeah, so what would the units be? Watts would it be? Or?
It would be like an enthalpy change, so it would be like kilojoules per mole would be one.
Sure. Kilojoules per mole, like that maybe?
Yeah.
Another one that comes up in MHF, we might see it, I can't remember for sure, which is a strange one, is centimeters cubed per centimeter. You could even have centimeters per centimeter, which is weird, but if you're talking about the relationship between two different kinds of change, one is changing a certain amount of centimeters and another one is changing a different amount of centimeters, but they're related in some way. It seems like a strange thing, but like you could have them. This one is, as I think the example was, imagine yourself, and this is actually a really good example before we move on to think about how these questions work. The unit is called related rates. So it's like there's some real world situation where there's a relationship between two kinds of rates. And as one is changing, how does the other change? These are the kinds of problems that we solve. So one from MHF goes something like you're blowing up a balloon with a consistent amount of air. So imagine you have an air compressor that blows a consistent amount of air. And you can imagine yourself just doing it with your mouth as well, but like that wouldn't be very consistent, but it will work for this demonstration. So but let's say you got an air compressor that blows air consistently, and you attach your balloon to it and start blowing it up. Well, in the very beginning, you're like the airflow is constant. So the amount of air in the balloon is changing, but it's changing at a constant rate, right? But in the very beginning, the balloon's going to blow up really quickly. And then after it gets to be a certain size, it's going to slow down in how it looks like it's increasing in size. The amount of air going into it is the same, but it's not increasing as much because it's already big, so it requires more air to make it grow even bigger. Does that make sense? So the radius of that balloon, if you imagine it to be like a sphere, changes quickly at first, but then slows down. The change in radius is changing over time, whereas the change in volume would be consistent. Does that make sense? And this is how these rates are related to each other. That's the kind of question that we could solve. And that one would have possibly units like this, centimeters cubed per centimeter. And MHF it did have that unit. In calculus, we don't tend to do them like this. You kind of could, but we don't tend to, so we won't see it as often. But rates can be strange. Okay, let's move on. We're going to do a couple of just practice questions because this stuff is different. One of the reasons why word problems are hard is because they tend to be a bit unfamiliar to us in terms of the kinds of things we're used to doing. So we have to get used to the way that these problems, just the mechanics of these problems and what they're like. We have to kind of adjust. Everything we've done in this course, starting from Unit 2, Unit 1 was limits, but Unit 2, when we started doing derivatives, almost every question, not quite everyone, some of the homework questions were different, but we took the derivative with respect to x. And it was something like, and this is actually going to be helpful, y equals 3x squared. So when I take the derivative of this, what is it? Well, when I take the derivative, in fact, we took for granted that we were always just taking the derivative with respect to whatever variable was there. You know what I mean? Like we took the derivative with respect to x every single time. So it would work out to something like this. dy by dx equals, who wants to do this one for me? It's super easy. I heard that 6x. Okay. And what we're doing now is no different, except it says differentiate each of the following with respect to t. So we're going to get to that in a minute. So there's something curious about that. But this is one of the things that is trickier about word problems. One of them is that sometimes the numbers are not as friendly. We're always working with nice round integer numbers. And then all of a sudden in word problems, I've got a pi there, like things are different, right? That's one of the reasons. But another one is sometimes just, even though it's the same rules, it's just an unfamiliar territory. And so the steps sometimes look a little bit different. What's curious about this question when it says take the derivative with respect to t?
T isn't in the question.
There isn't even a t in the question. So why would you do that?
Because you're relating it to something else where T isn't a question.
Yeah. What do you think t would represent? Time. So this is a question where things are changing over time. And our independent variable, time, is the thing that we're always going to take the derivative with respect to. So it's often time. It's not always. We're going to write this down in a moment. But if it's time, even though there's no t in the equation, you're taking the derivative with respect to t. So what would that look like? What is a? What does anybody know what this formula is for? Area of a circle. Very good. It's useful to recognize these. Some of them you're going to need to know. This is one that you need to know. I won't give it to you. If it's an unconventional one like a sphere or a cylinder or something like that, like surface area of a cylinder, I'll give you that formula on a test. But this is one you should know. Area of a rectangle, oh my gosh, you should know. Area of a triangle, you should know. Area, surface area, volume of like cubes or rectangular prisms, you should know. But if it was a cone or something like that, you might not know it. So we'd give it to you. What is the derivative of A, area, with respect to t? Seems like a strange question, but it's one that we need to be able to answer. Very good, dA by dt. Anything that's changing, any variable that's changing, you have to be paying attention to, observing it, noticing it in your formula, or when you write the formula yourself, that it's there. And it's a variable that you have to take the derivative of with respect to t or whatever it is. So which of the other things that are left in here are variables that are changing? Like, would area change over time? Yes. Does pi change over time? No. So pi is a constant. You can have variables and formulas that are a constant in the situation. And in that case, you would just sub in as a constant. Generally speaking, we don't. If it's a variable, it's a variable, it's a variable, but it's possible. So pi is a constant, so pi doesn't change. What about r? Radius, is that going to change? Yes? So that's what we have to pay attention to when we're taking the derivative of this. So does anybody want to guess at what the next part is? Now be careful. People think, well, pi is a constant, so it's gone. The derivative is 0. No. Just like when I took the derivative of this, notice how this is almost identical to that. 3x squared. Pi r squared. Pi is a constant, 3 is a constant. R is the variable, x is the variable, 2 was the exponent, and the 2 was the exponent again here. So I took this down and multiplied it. The pi doesn't disappear. So what's it going to be?
2 pi r times dr over ddt.
Very good. And I might have expected somebody to forget that part, but that would be our next point of discussion. Super important that you get that. This is the rate at which the radius is changing. This is the rate at which the area is changing. So dA is the change, in area dt is the change in time. dr is the change in radius. All of these things are changing in this situation. I mean, there is no situation because it's just a formula, but you know what I mean once we start getting into the actual problems. So dA by dt is the change in area. In fact, we're going to write this down again, so you don't have to write it down now, but over time. How does the area change as time changes? That's your rate. So what do rates look like as variables in calculus? dA by dt, dr by dt, dv by dt, whatever it is. Okay? Let's try one more. Does anybody recognize that? What's that the formula of? Volume of a cylinder, very nice. So the derivative of v is hopefully easy, dv by dt. Does anybody notice anything important about this one? So a pi, again, is constant, but it's product rule, very nice because it's got an r and an h. It's simple, and it looks like it should be super easy because it's such a simple formula, but it's product rule. So I mean, it's still not hard, but you got to be careful. Okay, so you could take the pi out. Some of you have done that in the past, where if you have a constant out front, you you take it out and you just leave it out front. I'll consider it as part of the p. So it's pi r squared times h. So the derivative of the first part is 2 pi r dr by dt times the second thing plus, what's the derivative of the second thing? What's the derivative of h with respect to t? Just dh by dt, very good. Times the first thing. This is just practice. We're not like, there won't be any questions like this on your test, but you're going to have to take the derivative of some formula or something every single time you do a problem. So this is just practice and noticing a couple of things before we actually get into the applications. So generally speaking, you're going to do this, and then you're going to substitute stuff in and start rearranging to solve. So the form wouldn't matter too much. Seems easy, I know, and I mean, there's nothing about this that's particularly challenging or hard, but in the greater context of these word problems, it can be tricky. It does get hard. Recognizing what each of these variables represents, again, I think people take it for granted. It seems simple. I think it's really important to explicitly think. H is the height. dH by dt is the change in height over time. That's the rate at which the height is changing in this situation, whatever it is. Like, make those statements to yourself in your head. Any questions before we move on? I'm going to write down some advice here. I suggest you write it down too, obviously. And I suggest that if you're ever stuck, you come back to this page, look at it, see if there's something you're missing or you haven't done, and use this as like not just advice, but tips, hints, steps to get started, steps to solve the question in general, that kind of thing. Things that you're going to be required to do to be successful in solving these. I'm not doing them in order. It's not a matter of actual steps, step 1, step 2, step 3. You can develop that yourself. Building good habits with this stuff over the next, like today and then over the next few days, I guess, I think will be key to, especially when they start to get harder and we start to mix them all up. The questions today are going to come across as easy. Don't be fooled. Okay? Not to say that this stuff is really hard. If you develop good habits, it can be quite straightforward. But you got to get those habits. You got to get the right method of thinking. So, advice. First thing we're going to think about is determine what everything is being compared to? So this is often time, but not always. And this is what you're taking the derivative with respect to. Generally, you're given a rate in the question, and you can use the rate in the units of the rate, which again are probably given to you, or maybe not explicitly, but they're there to determine what this is. If it's not time, when you read through the question, you should be able to figure out that that's the case. Okay, but often it's time, and so we're taking the derivative with respect to t. You're going to identify variables. I'm going to come back to this. Which ones are changing and which ones are not? Usually they're all changing. You're going to identify any necessary formulas. They might be given, they might be provided like on the side because you don't know the formula for volume of a pyramid or something like that. Or it might be something that you kind of have to develop, or it might be something like Pythagorean theorem or something like that. But you have to determine what formula is relating the things that are changing and the variables. And another really important thing is to identify what values you're given. So this is something common to you in science and physics in particular, I think, where you list out your givens and what their variable is. That's going to be really useful. If you can get good at that, that's one of the habits that can really help you. If you look at these questions as big picture stuff, they can be overwhelming. If you dial it in and you look at specifics like, I'm given this, this is the variable for this given, this is the formula, take the derivative and move on, and they become much more straightforward, I think. Okay? If you have ever solved a problem and at no point in the problem you took the derivative of something, you have not solved the problem correctly. So at some point you're going to differentiate. It seems funny and it seems obvious, but I've seen it many times where people have solved the problem and they haven't even taken the derivative of something. So that's kind of going to be key to solving these. It's not like, oh, this one's different, I can solve it without. No, you can't. Okay? So you've fooled yourself. One of the types that we're going to do on Wednesday is substitute. You don't always substitute. You don't necessarily have to substitute, but it's often a good idea to do it. So on Wednesday, I'm going to show you this technique and this trick, and part of your learning this week is knowing when to use it, when not to, I suppose. Okay, so it's not necessarily a rule that you have to, it's just a very good idea in some situations. Obviously, at some point, you're going to solve. What are you solving for? So identifying what you're solving for, and then you're going to have to solve. Usually that part is relatively simple. That's the interesting thing about applications as well, is they're unfamiliar. You know, they're sometimes not as friendly numbers. The question isn't as clear necessarily exactly what it's asking. You have to do the setup part. That's what makes it hard. Once you've got it set up, it's actually pretty easy. Compared to some of the derivatives of things we've been taking over the last couple of months, these ones and some of the equations that you solve, a lot of these ones are pretty simple once you get it set up correctly. Okay? So, and one thing that I wanted to add, we're going to see that sort of coming up. If something is changing, if a variable is changing, in other words, the thing the variable represents, like radius, if it's changing in the question, This is really important because people do it a lot and it's big time wrong. You cannot sub in for it until after taking the derivative. Okay? Really, really important. You come up with your formula. You probably don't do any substituting. If you're absolutely sure something is constant and in the situation not changing, you could sub in for it. And in fact, that would be a good idea. It would make things easy. But often everything's changing, and it's a very Buddhist philosophy. Everything in life changes. And so everything's changing, so you take the derivative before you start substituting things. Okay? And then we wrote this down, but I'm going to write it again, just also recognizing that dA by dt, like this is super key. What does that mean? So this would be the change in area over time. dr by dt. It's going to be the change in, probably. I mean, you don't know for sure what r is, but probably radius, right? D for distance is a little wonky because it'd be dd by dt, which is just even hard to say. So we often skip that. I do see it here or there, like you see it once in a while. It's not wrong to do that. But instead of d for distance, we would often use s for position. So ds by dt is the change in position or distance over time. And again, that's like speed, right? And look, kilometers, which is a measurement of distance or position, over hours, not t, over h, which is hours, which is a measure of time. So you can see the rate in the units, and you can see the units in the rate. And it's really useful to be able to go back and forth. And when I look at ds as the change in distance, I know that's units are kilometers. And when I see dt, that's change in time, I know its units are hours or minutes or seconds or whatever they are. And so I can make the units with that, or I can use the units to figure out what this should be. Really, really useful advice or habit or whatever to identify rates. Again, it seems simple, but trust me, it's not always going to be. Any questions on that? Let's get into some problems. The volume of a sphere is increasing at 100 centimeters cubed each second. Find the rate at which the radius changes when it is 25 centimeters. So we're going to do some identifying here. I wouldn't always, like I'm going to really identify stuff and point stuff out here. I wouldn't always do this personally. You obviously can, some people like to if you want, but I'm just doing this because it's our first example. So it doesn't give me the volume, but it gives me something about the volume. 100 centimeters cubed each second. It also tells me it's increasing, and it tells me that it's the volume. So this is a rate. And it's a given that it's the rate at which the volume is changing. So I would call this dV by dt. And it's centimeters cubed per second. Centimeters cubed is a measure of volume. I can just see that on its own. Second is a measure of time. So this is obviously volume over time. Change in volume over change in time. dV by dt. So dV by dt is increasing, so it's positive 100 centimeters cubed per second. Then it says find the rate. So that's telling me what I'm supposed to be finding. Again, that's something you have to identify. And it's asking me to identify the rate which the radius is changing. So what would be the rate of the radius changing? Zach? dr by dt, good. That's what we're finding. And then finally, it's telling me that the radius is 25 centimeters, so that's another given. That's not a rate, so it's not d something by d something, it's just r. So I'm going to write all of this down on the side. We're supposed to find dr by dt when r equals 25 centimeters. Okay. What's the formula for volume of a sphere? Does anybody know? Close? Very close. Anybody know what to add to that?
4 over 3 pi.
Yeah, 4/3 pi r cubed. Good. What's changing in here? We can't see, this is what people want to do. They want to take 25 and put it in for r. But r is changing, so you can't do that. Okay? If this was some kind of shape that always had a radius of 25, then you could sub it in. But that is changing, so you cannot do that yet. So we do that after. We're going to take the derivative of this. V is changing, r is changing. 4/3 obviously doesn't change, pi doesn't change, so I only have those two variables. So this is dv by dt. 3 times 4 over 3. 3 is divided 1, so that just ends up as 4 pi r squared. And always don't forget, what are we forgetting? We're actually forgetting the thing we have to find, right? dr by dt. This is the part that is different, but it happens every time. And like I said, that's what you're finding. So if you didn't have that in your equation at this step, you'd be like, well, how can I find it if it's not even there? So hopefully that would be enough for you to say, like, I guess I missed that part, or I've set something up wrong. In fact, remember, I'm going to go way back up. We talked about this when we started doing implicit differentiation. Technically speaking, when I take the derivative, I would have a dx by dx, but that's just 1, so I don't have to do it because I'm taking the derivative with respect to x, right? But in this case, I'm taking the derivative with respect to t, and this is talking about r. Now that I've taken the derivative, I can sub in. So it's 100. I'm going to divide both sides by 4, and I get 25 equals pi times 25 squared. I'm only doing this to show that I can then divide one of those 25s with one of those. And when I move these over, I get 1 over 25 pi equals dr by dt. So that's what I mean by that. Solving works out to be fairly simple, doesn't it? What is dr by dt? Like, what have we found? The change in radius over time, which is what we're supposed to find. But like, if you think about what this represents, you can understand what it is you've found in case it's not the thing you're supposed to be looking for or you haven't already thought of it. And what would radius be measured in? centimeters. And what is time measured in this case? Seconds. So this is 1 over 25 pi centimeters per second. Generally speaking, you would do exact answer in terms of pi, if there's a pi in the question. You may also be asked to round to some decimal places. That depends on the instructions, of course. We always end with a therefore statement, and there's something really important about the therefore statement. We interpret our answer. The ones we're doing today, I think they're all positive, which is kind of unfortunate, but what if it works out to be negative? Bradley? That would be decreasing, and you must say that. You can't say, therefore, the radius is changing at -5 centimeters per second or something like that. You would have to say it's decreasing at 5. So your instructions on assessments or whatever, and in your homework and all the solutions, you'll see the solutions are always written out in the therefore statement as a positive rate, but interpreted to be either increasing or decreasing or going one way or going the other way or something like that. Therefore, the radius is increasing at 1 over 25 pi centimeters per second. Okay, let's try a few more. So this one's a bit different. If you didn't quite understand even what it was asking, like this is the kind of thing where you could read through this question, you'd be like, I don't know what it's saying. I don't know what it's asking me to do. I don't understand what's happening here. What does my life come to? Maybe, I don't know. But like, if you can break it down into the little steps and think about, well, okay, it says the length is decreasing. That's a change in length. What would be the variable that I could write out for that? You know what I mean? And you can take this sort of muddled mess of a situation and turn it into variables and write a formula and just solve it, maybe without even totally understanding what's happening. That being said, I'm going to show you what's happening. So let's read it the whole way through first, and then I'm going to do a little visual of what's happening here. Because if you can visualize it, it can also be helpful, in a lot of cases at least. So it says the length of a rectangle is decreasing by 1 centimeter each second, while the width is increasing by 2 centimeters each second. Find the rate at which the area is changing when the rectangle becomes a square and both length and width are 10 centimeters. So this is what's happening. And I designed this so that it will turn into a square of 10 centimeters side lengths. So you can see that the width is 2 and the length is 14. And when I go 1 second, the length has decreased by 1 centimeter from 14 to 13, and the width has increased from 2 to 4 because it's increasing by 2. So 2, 4, 6, 8, it's increasing by 2 every second, whereas the length is decreasing by 1 every second, 14, 13, 12. And then at some time, after a few seconds, they're both 10, and it's a square. And now, go back and look at how the area is changing. Like this has an area of 28. In fact, this is the area over here. And so it's increasing, 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 and then decreasing, 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 decreasing to 0, I guess, eventually. Okay, so you can see how the area is changing over time, and it's changing at different rates over time. But the side lengths are both changing at consistent rates, increasing and decreasing. So that's what's happening. This is what we have to do. So let's start writing out our givens. The length of a rectangle is decreasing by 1 centimeter each second. How would I write that? What would be the change in length?
dl over dt equals -1 centimeter.
Very good. And that's key. And that is -1, whoops, not meters, centimeters per second. And it's dl by dt. Recognizing that that's a rate, and so that's change. And we're going to be doing the change in length over time. The fact that it says each second is what tells me that time is what everything's being compared to, right? And everything has to be compared to the same stuff. The width is increasing by 2 centimeters each second, so that's going to be dw by dt is positive 2 centimeters per second. Find the rate at which the area is changing. So what does that mean? dA by dt. When the length and the width both equal 10 centimeters, and it's a square. What's the formula for this one? This is one that you need to know. It's too easy, nobody wants to answer. Just length times width, so the area of a rectangle is length times width. What do you notice about that? Taking the derivative with respect to t. Product rule again. Like it's the simplest little formula, but it's product rule, and if you didn't notice that, then everything would be out the window, right? So dA by dt, and maybe you're starting to see how like the familiarity of this stuff is different, it's unfamiliar, and it's a bit quirky, so that's part of what we're getting used to. So derivative of L is dL by dt times that's the derivative of the first thing times the second thing. So the second thing is W plus derivative of the second thing, which is dW by dt times the first thing, which is L. I'm finding dA by dt. See, this is what I'm talking about. If you were just big picture and you're trying to work it out, you wouldn't really know what's going on. We've already written down that we're finding dA by dt. So I already know I'm not subbing in for that. That's what I'm solving for. So I sub in for everything else that I've written out over here. dL by dt is -1. W was 10. dW by dt was the change in width was 2, +2, and L was also 10. And so this is where now it's really easy. -10 plus 20 equals 10. And it's dA by dt. A area would be centimeters squared. T is seconds, so centimeters squared per second. Does that make sense? We'll take a look. Right before it becomes a square, I'm at 88, and then it's 100. So it was more than 10 because that's not a second. This is an instantaneous rate of change. You wouldn't expect it to be identical to the change that you would see here, but you would expect it to be similar. So it was 12 before, and it was 8 after. So you could see that sort of the middle of that would be 10, right? Therefore, the area, again, is increasing at 10 centimeters squared per second. You don't have to write out the units both times. You don't have to write them out twice, but you got to be thinking about units, and it helps to relate the rates the way we write them here to the units and all that kind of stuff. You could. I would recommend using meaningful variables. I think it's easier on your brain when you've got a W for width, but there are cases where you wouldn't have something obvious, so you would use X and Y or A and B or something like that for sure. And you could use whatever you want as long as it's clear. Okay, couple more. The area of a circle is increasing by 30 centimeters squared each second. Find the rate at which the radius is changing when it has a length of 5 centimeters. Why don't you give this one a try? So again, you need to know what steps to start at. If you just look at that and you start trying to think, what am I going to do? You want to find your givens, name them properly, think about what you're trying to find, think about what formula relates all of the parts in this situation. and just pick it apart one little bit at a time, and then it starts to come together. The area of a circle is increasing. So the area is changing. What are we going to call that? dA by dt, I think. And it's 30 centimeters squared per second. We're finding the rate that the radius is changing. So what's that? Good. So we're going to find dr by dt when the radius has a length of 5 centimeters. And we've already seen this, but again, what is the formula for that's going to be relevant here? Pi r squared. So area of a circle, obviously, area equals pi r squared. I can't sub in r now because r is changing. As the area changes, it tells us the area is changing. If the area of a circle is changing, obviously its radius is changing. So after I've taken the derivative, now this is the formula that relates the change in area to the radius and the change in radius. So now I can sub that in because I'm trying to find this when r is 5. But r could be 4, or r could be 3, or r could be 2. So if I subbed in here, r becomes a constant. I wouldn't even have the dr by dt in it, right? So you really got to be careful. It's a common mistake. So let's see. I've got 30 equals 2 pi times 5 dr by dt. So dr by dt equals 30 over 2 times 5 is 10 pi, which is 3 over pi, and our radius is just centimeters. T is in seconds. Therefore, the radius is increasing at a rate of 3 over pi centimeters per second. Got to say increasing, decreasing, or something to that effect. We good? Last one has a little bit of the second part has a bit of a twist to it, like it's a little bit different. Otherwise, it's still fairly straightforward. This one is also different from the other example that we talked about where it was area of a rectangle, but that one was the length was decreasing and the width was increasing. So it was a rectangle that became a square. This one is a cube that remains a cube because all the side lengths are increasing together at the same rate. So this is a cube that's just getting bigger, 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 whatever that means. They're all increasing by 10 centimeters. So we don't want to call, because and it's a cube, so that also tells us they're all equal. And they're all changing at the same rate. So we don't want to do length times width times height, because then we'd have 3 variables, and that would be like extended product rule. We're going to use 1 variable for all the side lengths, right? So let's think about what we need. Let's see. The sides of a cube are increasing. So if I call the S, let S represent the side lengths. I'm going to use S for all of them. They're all the same. And they're increasing by 10 centimeters per second, so ds by dt is 10 centimeters per second. So then question A is asking about the area, which is like surface area, but we'll just use A to simplify the notation. So it says find the rate. So we're finding dA by dt when S equals 1 meter. Careful, the other thing about this is they're in different units. These two of them are in centimeters, like part B has a part that's in centimeters. This is in centimeters, this is in meters, so we have to obviously put everything into the same unit. So when S equals 100 centimeters, which is 1 meter, we're going to find the change in area. Okay? What would be the formula for area or surface area of a cube? This is one that you probably wouldn't be given. You should be able to work through this and think it up for yourself. Dana?
6s squared.
So there's a cube has 6 sides. Whoops. So 6, and each side will be s times s, length times width of it. So 6s squared. Very good. Take the derivative. So we're finding dA by dt when s is 100, ds by dt is 10, so I've got all the givens that I need. I suppose if you took the derivative and you were missing something, like you had a variable in your step here that you didn't know the value of, you either missed it or you've set it up wrong, or there's something extra that you need to think about. Go back and figure out what the missing thing is. That's sometimes an extra step. So this works out to 12,000. And it's area, so centimeters squared per second. And again, therefore, the area is increasing at 12,000 centimeters per second. Centimeters squared per second. Okay, so that one was straightforward. Is everybody okay with that? A few minutes left to finish our last one. This is all we need. What's different about B? So B says find the rate at which the area is changing when the cube has a volume of 4,000 centimeters cubed. What's wrong with this? Take a look. This is still the formula we're going to be using because it's still talking about area. This doesn't have volume in it. The requirements for this formula are ds by dt, which we have, and s, which we don't. It gives us volume. The last question gave us the side length it wanted. This one doesn't, so what do I have to do? Yeah, so what is volume of a cube? Yeah, but let's start with the volume formula. So V equals S cubed, right? And V equals 4,000 is our given. So sub that in, and you're exactly right. Take the cube root. So now we're finding dA by dt again at that side length. Had we not already done the first question and realized that we need side length, this would be a harder one. Out of context or all on its own, this would be a little bit trickier. It wouldn't be as obvious, I think, straightforward. But it's one of the kinds that we do, one of the kinds that we practice. So after practicing it a bunch of times, you get used to the fact that, well, it doesn't give me the side length, but it gives me volume, and I can use that to solve for the side length. So it still becomes one of the common tricks. And in this case, you wouldn't do this exact value. The question would probably say round to such and such, because we write things in terms of pi often. We don't write things in terms of the cube root of 4,000. It works out to about 1904.9 centimeters squared per second. And again, therefore, the area is increasing at that rate.